Humanity has detected over 5,500 exoplanets, but it's just the beginning. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. We're diving into the astounding science of exoplanet detection this week, exploring some of the worlds that we've discovered beyond our solar system. Our guest, Jessie Christiansen, is the project scientist for NASA's Exoplanet Science Institute. She'll share some of the latest breakthroughs in the field and discuss her role in hosting Caltech's new podcast and web series, Explore Exoplanets, The Discoverers. Our science editor, Asa Stahl, will tell us a little bit more about the upcoming Habitable Worlds Observatory, a cutting-edge space telescope that's in development and designed to hunt for worlds that could harbor life. We'll also bring you the latest news on the International Space Station, including updates on the Boeing Starliner crew and the contract to deorbit the ISS, with our senior communications advisor, Matt Kaplan. And don't miss our regular feature, What's Up with Bruce Betts. We'll talk a little bit about exoplanet detection and share a new space station-themed random space fact. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. Well, let's kick this off with the International Space Station. On June 5th, 2024, Boeing's Starliner spacecraft conducted its first crew flight test. It carried NASA astronauts Butch Wilmore and Sunita Williams to the International Space Station. On the way to space, it experienced multiple technical issues, leading to an indefinite delay in its return from the ISS. So what are Sunny and Butch up to now that their short trip to space has been extended? Matt Kaplan, our senior communications advisor and the creator of Planetary Radio, is here with the details. Hey, Matt, welcome back.
Always glad to join you again, Sarah.
Well, you were just here a couple weeks ago, and we were talking about the successful launch of the crew flight test for Boeing's Starliner. And it was only supposed to be a 10-day mission, but due to technical difficulties, here we are. It looks like it might be a whole summer break aboard the ISS. What's going on?
Shades of Gilligan's Island, a 3-hour tour. It's getting longer and longer. But what's going on is that they basically have had a very successful test so far, and they have had a couple of problems. One with some of the thrusters, and two with helium leaks. Helium is, notoriously difficult to keep in one place because of little tiny molecules. And thrusters, they have lots of thrusters, but they still want to make sure these work. And it's really important to note, the problems they've encountered are on the service module, that unit or module that's hanging on the rear of the capsule, which they're going to release before they re-enter. And so if they're going to figure this out, they have a much better chance of doing that while the service module is still part of Starliner, and they can run a lot of tests on the ground. I mean, they are also going to test some of these thrusters in White Sands, New Mexico, and see what they learn there, try and simulate it in a chamber and play with it some more up there on orbit.
Well, even if we figure out what the issues are, what caused them, it's not like we can fix those problems while they're in space currently. What happens if we determine that it's not actually safe for them to come down in this capsule?
Yeah, they're not stranded, as you might think if you had read certain headlines a week or two ago. There are certainly lots of other ways to get down. There's a Soyuz capsule sitting there. There's a Dragon capsule sitting there, although how embarrassing that would be for Boeing, for the astronauts to have to come down in the competitor's reentry vehicle. And NASA says they're still very confident that Starliner is going to make it back down to Earth with Sunny Williams and Butch Wilmore. They have a 10x safety margin, so they feel pretty confident about that. They just want to work these things out. But if worse came to worse, they can still get home.
What are Sunny and Butch actually doing while they're on the ISS? Because they weren't supposed to be here this long. Did someone give them extra homework?
Yeah, you might say that. They're on all kinds of details. They keep the ISS astronauts and cosmonauts very, very busy. And so they're very happy to have 4 more hands up there to help get science done and maintenance work done and, dusting, I suppose. And they're happy to be there. I mean, Butch and Sunny they both lived on the ISS, and they apparently are thrilled to be back. I don't know, maybe they'll get a little tired of this after it stretches out for a while longer. And they probably are going to be up there for quite a few more weeks as NASA and Boeing try to figure all this stuff out. So I don't know, maybe they'll get a little homesick. But so far, they seem pretty thrilled. And I got to say, I'm envious.
Who wouldn't be? Extra weeks just hanging out on the ISS. I mean, I know it's a lot of work, but what fulfilling work. And then you get to take your break out in the cupola, staring out at the Earth.
Man. Yep. Just staring down at that big blue marble.
Does it put any strain on the supplies on the ISS to have 2 extra people for that long?
A little bit, but not terribly. I mean, there are regular supply missions, and apparently the life support on the ISS is able to handle a couple of more people pretty easily. So not that I have heard of. No, I think the air conditioning is still working fine.
It's got to be such a bummer for everyone over at Boeing to spend all this time to build this spacecraft, to have what was seemingly such a successful launch be tainted by this relatively minor issues with the thrusters and a helium leak. Everyone's going to remember this as a moment that Boeing got 2 people stuck on the ISS, but really this is a moment that we should be kind of celebrating. They've done a pretty good job other than this, obviously.
Yeah, we heard much the same from Mark Nappy, who's a vice president and program manager for the commercial crew program at Boeing. And we've got a little bit of what Mark had to say as he has been following the coverage of what's going on up there with Starliner.
Well, let's take a listen.
Every morning I've got Google alerts set and they send me Starliner stories. And so every morning I sit and I read them, and I'll tell you, from being a representative of Boeing and a representative of the Starliner program, it's pretty painful to read the things that are out there. We've gotten a really good test flight that's been accomplished so far, and it's being viewed rather negatively.
Yeah, that's a bummer. At the same time, I mean, I'm really glad that there was an extra capsule aboard the ISS during this moment, because just last Wednesday on June 26th, there was an issue where I believe it was a Russian Resurs P-1 satellite broke up while it was in orbit, and all those pieces could have potentially put the people on the ISS in danger. So the people on board actually had to take shelter inside some of these capsules, and having one more place to go hide out, probably a good idea.
Yeah, where was Sandra Bullock when they needed her on the ISS? You're right. All of them, including, of course, Sonny and Butch, climbed into their little escape capsules. And, like I said, there are 3 of them up there now, Starliner and a Dragon and a Soyuz. So good to have 3 lifeboats. But, this certainly was another demonstration of just how dangerous it can be to have debris on orbit.
And we're just going to have more and more issues with this as more objects go out into space, especially as we get more of these satellite constellations, 20,000 satellites at a time. We really need to make sure that we can deorbit these things. Which brings up another topic, which is that even the ISS itself can't stay in space forever, as much as we'd like. And there's been a lot of discussion about deorbiting the International Space Station for a while. They're going to be targeting a place in the ocean, which is very far away. It's literally the furthest you can get away from a place to live on Earth. Even the ocean itself there is very deoxygenated, so there aren't a lot of fish or anything. But they finally issued the contract for who's going to be bringing down the ISS. What's the scoop on that?
SpaceX got that contract, and it remains to be seen exactly what the technology will be, but it's a very sizable contract, and they're now hoping that the ISS is going to be just fine until roughly 2030, but it is getting kind of creaky. Space is hard. Space is hard on stuff that's in space. It, starts to get a little iffy about keeping the ISS up there much longer than that. And so the trick will be, as you've said, SpaceX will need to design a vehicle that can get the ISS headed back down to Earth in a very controlled way and come down on that spot in the ocean where, hopefully there won't be any very unlucky fisher people in the way, because, there are some pretty hefty, pretty massive pieces of the ISS. It is not all going to burn up.
Yeah, Point Nemo is the place where we send all those giant things from space. There have been many large objects from space deorbited down to that point, but still, I wonder what lies beneath the ocean there. Maybe someday someone will find a way to dig those all up and take a look at them.
I'm going to help with that salvage work.
What do you think are going to be some of the biggest challenges in deorbiting something that large? I don't think we've ever attempted something like that before. Wait, actually, there was a Russian space station that we did.
That's right.
In the past. Yeah,
that's right. A couple, actually, Salyut and Mir, and for that matter, Skylab, which was not in the same category. I mean, nothing touches the ISS for just a mass of human-created object in space. So it does present special challenges. I mean, how do you do this gently enough so the pieces don't start breaking off? I mean, after all, you have giant solar panels attached by hinges or joints, and you need to make sure that happens. My guess is there'll be a lot of work initially just to remove all the volatiles, remove everything else of any volume, and send them back down on Dragons and, one would hope, Starliners, and who knows, maybe Dream Chasers by that time, since they're still looking to do their first cargo test sometime in the next year or so. But it's going to be a major, major effort like nothing we have ever seen before.
It's so sad to think that the ISS has to come down at some point, but it has to, and we're looking forward to a whole future of new space stations. At some point, we'll have the Lunar Gateway. I'm really looking forward to that once we have something in orbit permanently around the moon. So as sad as it is, this is going to be an interesting thing to test, and a big moment for all of us space lovers to send off the ISS for everything that it's done. But we don't have to worry about that yet. We got a few years, so no crying about it just yet.
Don't forget those commercial space stations that are currently in development. Several companies wanting to, for some of them at least, park them right next to, even have them docked to the ISS before they break free. They'll be able to wave goodbye as the ISS comes home.
What a moment in history. Commercial space stations. It's very 2001: A Space Odyssey.
You bet. I want to ride that Pan Am shuttle.
Well, thanks so much for the update, Matt.
You bet, Sarah. And as I said, always a pleasure.
Now we turn to the field of exoplanet detection, the hunt for worlds beyond our solar system. Astronomers are currently limited in their ability to directly image exoplanets. We've discovered thousands of exoplanets, but most of them haven't been seen directly. Instead, astronomers use clever techniques to find them, like noticing when an exoplanet passes in front of its star, or measuring how the star wobbles due to the exoplanet's gravity. In a few cases, researchers have actually managed to directly image worlds, but it's immensely challenging, especially with smaller exoplanets. Even with the advanced optics of the James Webb Space Telescope, or JWST, directly imaging is limited to larger worlds like gas giants. But a new proposed telescope, the Habitable Worlds Observatory, could help us overcome these challenges. Here's Dr. Asa Stahl, our science editor, with a look forward at the Habitable Worlds Observatory and what it could mean for our search for life. Hey, Asa, welcome back.
Hey, thanks for having me.
We've got a lot of wonderful space telescopes out there, and we've made some really amazing advancements in the search for life. But now we have a new telescope to look forward to, the Habitable Worlds Observatory. Can you tell us a little bit about what this telescope is going to be doing?
The Habitable Worlds Observatory is essentially going to be NASA's flagship telescope of the 2040s, equivalent in the impact of James Webb Space Telescope or the Hubble Space Telescope, except it's going to be mainly targeted at discovering Earth-like planets around stars similar to the sun and looking for signs of life on them. It'll do other science too, stuff on galaxies, black holes, solar system science, but that is going to be its bread and butter, and that's where it's going to revolutionize astronomy and potentially society.
It's currently really difficult for us to directly image planets at all, let alone planets that are Earth-size, and then let alone analyze their atmospheres. What's different about this telescope that's going to allow it to do this kind of science?
Well, it's going to be space-based with a huge mirror, probably about 6 meters wide, and it's going to have an incredible coronagraph, which is an instrument designed to block the light from a star while leaving the light from really near the star where the planets are. So essentially, these planets that this observatory is going to be looking for will be billions of times, if not tens or even hundreds of billions of times, dimmer than the stars themselves. And so having that technology to block the starlight and retain the scattered or radiated planet light will be the real challenge of this space telescope.
And we've tested a mirror of this size on a telescope like JWST in the past. We had to fold it all up and put it inside of a rocket, so that created a lot of complexity. But we're also going to be able to test this coronagraph ahead of time, right?
Yeah, exactly. It's going to be deployed, the exact same coronagraph, on the Nancy Grace Roman telescope when that launches, or at least potentially the exact same coronagraph. I suppose they might develop it a little bit more between. But there'll also be all sorts of other ways in which NASA and other scientists will be able to develop and test the technologies that are going to lead up to this telescope before it launches. And that's part of why there's going to be decades before it's good to go, not just the amount of science and design that's going to go into it, but just how cutting edge it's going to be, that we don't even have a lot of the things that are going to be launched with it. We don't have those capabilities quite yet, but we know that we will have it by then. So for example, you were mentioning before, James Webb Space Telescope had to be folded up to fit within its launch vehicle, which was an Ariane 5 rocket. And that added a huge amount of complexity and made it a lot harder to design, took a lot longer to design, and was a lot more expensive than it would have been if it didn't have to do that, if NASA could have just built it and then, plopped it in space the way it was. Future telescopes, like maybe the Habitable Worlds Observatory, will have different launch vehicles to work with. For example, SpaceX's Starship has a much bigger payload capacity, just volume-wise, than an Ariane 5. And so you can imagine that in some ways it could get easier to deploy telescopes like this, even as they get more advanced. And at the same time, space agencies like NASA are always learning from their past missions how best to manage these trade-offs, how best to design future observatories, trading off things like, do we want to be serviceable or do we want to be redundant and just be this fortress that we can park in space and last for 50 years? But yeah, these are the kinds of things that I think we can look forward to seeing develop bit by bit over the next 20, 30 years. And, if you're feeling impatient already about when this thing is going to launch, at least know that there's going to be lots of fun things to watch on the way.
You actually just released a Search for Life class on our member community, so you're pretty familiar with where we're at in the search for life. You said earlier that this thing is going to be looking at least 25 exoplanets, but what are some of the things that we're looking for on these exoplanets that could indicate life to us?
So generally, atmospheric gases, we're tracing the contents of these planets' atmospheres, things like diatomic oxygen or ozone as a tracer of oxygen, methane, carbon dioxide, water vapor, and carbon monoxide as well, maybe. Those are probably the stars of the atmospheric show that people would be most interested in looking at. But there's all sorts of other gases that scientists will try to look for. And none of those in themselves, it's not like, if we see oxygen in the atmosphere of a distant exoplanet, that doesn't immediately mean that it has life on it, that it has plants that are photosynthesizing, or if there's water vapor, that doesn't mean that there's necessarily oceans. It's not that simple, and scientists will have to study these plants in extreme detail and really understand the context of the signals that they're getting just from the atmosphere. Then they'll have to build a really cohesive model of, we see that there's this much water and no carbon monoxide and a bit of oxygen, and it's around a star that has this kind of radiation, and that all tells us that it has life, or that all tells us that it makes no sense for it to have this kind of atmosphere that we think it could have. Each of these plants will be an incredible puzzle in themselves to unlock. You mentioned before about it'll discover at least 25 Earth-like planets around sun-like stars. That's the hope. That's the goal. But we actually don't really know for sure, because we're still not sure just how common Earth-like planets are in the habitable zones of sun-like stars. And so if those kinds of plants are extremely rare, which is unlikely given the sort of range of possibilities that we're aware of right now, then habitable worlds would have a much harder time. It's also possible that it's the other end of the range, and they're extremely common, and habitable worlds will be able to detect even more. The 25 is just kind of the best guess right now.
I think what's valuable about this is that it's not just going to be looking at exoplanets that are far beyond our solar system, but it's also going to be studying the potentially habitable worlds in our outer solar system. And then we can compare the two. Because then if we can actually travel to those worlds, see what the spectra looks like, and then observe what we can up close, that'll give us more of an understanding of what the spectra actually means when we're looking at other worlds. But even then, we're going to have to do an incredible amount of science to really understand what's going on in these planets.
Yeah, I mean, there's always that sort of beautiful complementary relationship between solar system science and extrasolar discoveries where, you get the amazing diversity and sample size of these distant, faraway systems, but then also you can study what's here in so much more detail and then extrapolate from that. And it's really cool to see one or the other. If we can imagine having an entire world like Titan or Europa around some distant star and seeing that and being like, oh, that looks like Titan or whatever. That looks like Venus. That looks like Mars. We already sort of do this right now, right? We name planets off of what we have in our own solar system. And yeah, I think it'll be incredible that Habitable Worlds Observatory will be able to do something like that. To me, the most exciting thing about it, beyond just the sheer potential of this thing could actually find life, outside of the solar system. If you ask most astronomers, what is the best bet? What could actually do it? And we're not talking about within the solar system, in which case someone might say, Dragonfly or some probe to Europa or something, or on Mars or Venus. But outside the solar system, what's our best bet? The Habitable Worlds Observatory. And even then, the cherry on top is that it could find nothing. It could find no evidence of life at all, and it will still probably be able to look at enough Earth-like planets around sun-like stars that if it finds nothing, it would still tell us something about the prevalence of life on such planets. We're already getting to the point where we know how common planets are, how common sun-like stars are, how common Earth-like worlds are around sun-like stars. We're just kind of pushing that now. And with Habitable Worlds Observatory, we will just start to get a sense of what the number is for, given an Earth-like planet, what's the possibility of life? How common is that? And that will be so cool. And to know that that's almost guaranteed is incredible.
Definitely worth the wait, even if we're all going to have to sit here and hope and just, wait for all the designs to go through and get that green light. Hopefully the 2040s or maybe the 2050s will get this. It'll be worth it.
Totally. It's going to be a crazy adventure to build a space telescope that looks for life on other planets. And it's not all going to happen literally in the clean room. It's going to happen for the years leading up to that too.
I'm so impressed with humans. The fact that we're even at this point where we can begin to do the science and even begin to try to create an instrument capable of doing something like this is so far beyond what I ever expected we would be able to do in my lifetime. And I'm really grateful. This is going to be really exciting.
Yeah, that's a really good attitude to have. I love it. A lot of people, I think, when they hear about, 2040s, we should just be grateful that we're capable of this and that we're able to do this sort of thing and that we are investing in it and it is going to happen. And I think I'm happy to just sit back and let these geniuses do their work.
Well, thanks so much, Asa. And who knows, maybe you and I will get to go high five at the launch of this thing someday.
Oh, yes. Looking forward to it.
In the past few decades, exoplanet detection has exploded, transforming from a niche field into a major astronomical endeavor. While the first exoplanets were discovered in the early 1990s, technological advancements and new detection methods have led to an exponential increase in discoveries. As of the recording of this show, scientists have confirmed 5,678 exoplanets, but it's just the beginning. There are a lot of exoplanets that we've made detections on but haven't confirmed yet, so that number is going to increase rapidly. Ground-based and space-based telescopes like Kepler and the Transiting Exoplanet Survey Satellite, or TESS, have played a crucial role, revealing thousands of exoplanets through transit photometry. The development of advanced spectrographs has enabled astronomers to detect the subtle wobbles in stars caused by orbiting planets. But this technology has also allowed us to study the composition of atmospheres of these distant worlds. These advancements have increased the number of exoplanets, but also revealed a vast diversity of planetary systems. From scorching hot Jupiters that orbit perilously close to their stars, to super-Earths, rocky exoplanets that are larger than our own, the variety is immense. Mini-Neptunes, the most common type of exoplanet that we've found so far, are unlike anything we have in our solar system. There are even lava worlds with molten surfaces and rogue planets that wander the galaxy unbound to any star. This rich assortment of worlds that we found is not only a testament to all of the people that have pushed forward this field in the last few decades, but it bodes really well for the future. There are so many discoveries just waiting to be made. Our next guest is Dr. Jessie Christiansen. She's the project scientist of NASA's Exoplanet Archive and the NASA Exoplanet Science Institute at the California Institute of Technology, or Caltech. She's also the most successful woman planet hunter in the world. She recently began hosting Caltech's new web series and podcast called Explore Exoplanets, The Discoverers. She'll tell us more about the ongoing quest to discover more worlds beyond our solar system. Hi, Jessie. Thanks for joining me.
Thanks so much for having me, Sarah.
I actually, when I first got into school, I wanted to study exoplanet detection. And strangely enough, right as I was getting into it, the Kepler Space Telescope took off and completely changed the field. So it's really cool speaking to someone who got to be such a big part of that mission.
Kepler was obviously a huge part of my life. When I started university, I didn't think I would look for exoplanets, actually. I started a biotechnology degree, which very interestingly, given the direction of exoplanets, might come in handy at some point, given that we're starting to think about things like biosignatures. But yes, I didn't think about exoplanets at all until I was at college and realized people were doing it. People were finding exoplanets around other stars. And I was like, oh my God, that sounds like the coolest thing one could possibly do. I want to do that.
Well, it's a perfect moment to get into the field. We are at the point where we've detected over 5,500 of these exoplanets, but strangely enough, that is kind of just the foundation of what I think is going to come later on as our technology advances, because there are so many worlds out there.
Yeah, it's really interesting, thinking about the amount of space, even just within our galaxy, that we've been able to explore so far. So, we have our solar system with our sun and our 8 planets, and our sun is just one of 100 billion stars in our galaxy. And the galaxy is this beautiful big spiral galaxy. You've seen images of it before. We've searched like a tiny bubble, just centered on our sun. We've searched a very small bubble of the galaxy. We've already found 5,500 planets. And one of the coolest things is you can do statistics from that. You can infer how common planets are. And we think most stars have planets, which is bananas.
I mean, considering that we have at least 8 in our solar system. I know we're still hunting for planet 9 if that exists, but as a bare minimum, I mean, that seems to suggest that it would be shocking if other stars didn't have other worlds around them. How would that even happen?
I think until you see it, it's hard to draw strong statistical conclusions, right? Because, the thing you just said, we have 8, why aren't there everywhere? You could make the same statement about life, right? Like, there's one habitable planet in our solar system and it has life on it. What does that mean for the statistics? What does that mean for how common life is? So it's tempting, right, to take our solar system and be like, well, this is probably pretty standard, right? Like, I think one of the things we came away from the Copernican revolution in, you can't just pretend that the sun is special and the earth is special. Like, we're pretty boring. We're pretty ordinary if you look at all the other sun-like stars in the sky. So the fact that they all have planets, check, that's great. But we don't know the second question. Do they all have life?
Also, what types of worlds are out there that we haven't been able to get a good statistical understanding of just because of the limitations of our technology? And usually the way that we find these worlds is by watching them transit across their stars, which means necessarily we're very limited in what we're seeing, because who knows what angle those planets are orbiting their star at. There's so much we're missing.
Yeah, I would say that's a super cool thing about having been involved in the field for 20 years now, is every time a new detection technique or a new instrument that's better at a previous technique comes along, we find whole new things, like whole new populations of planets in places we didn't expect, around stars we didn't expect, in configurations we didn't expect. Basically, every time we can peel back another layer, we're surprised. And that's just, as a scientist, that's just joyous, right? You're just like, oh my God, of course, nature has a better imagination than we do. Look at all of these incredibly different and interesting planets we found.
Well, one of the cool things I learned about you is that you're actually the most successful woman planet hunter in the world. How many worlds so far? How many worlds have you found?
I have found 66 published confirmed planets, although I will let you and our listeners in on the fact that one of them we have found out since is not a real planet. It's actually a star on a slightly different orbit. And so when that gets published, that paper's being worked on now, it will go down to 65. But I'll still hold my spot.
Well, there are so many of these worlds that we detect. We think that they're planets, we confirm them, and then we learn more. And there's an even broader number that we've detected but haven't yet confirmed. So who knows if your number will go up ultimately.
I hope so. I'm still looking.
From your perspective, how has the technology in detecting and studying these exoplanets evolved over the course of your career?
20 years ago, when people were, radial velocity was the technique that people were using a lot 20 and 30 years ago, which is detecting the wobble of the star as the planet is orbiting around it. There were these breakthroughs 20, 25 years ago with iodine cells and thorium argon cells to imprint wavelengths on the spectrum so you could calibrate it. But we quickly realized that that wasn't good enough. So then over the last 20 years, it's been this incredible, how can we calibrate this better? And now they're using things like laser combs, where they actually have lasers at very, very precisely calibrated wavelengths, imprint this grid on the spectrum that lets you very carefully calibrate it. So just all of the cool ideas that people have come up with, different kinds of detectors, different kinds of telescopes. And then even from something like the transit technique that you mentioned, the planet goes in front of the star and blocks some of the light. Now, that's a pretty basic measurement, but there's so many different things people have worked out how to do with that, right? You can look into the planet's atmospheres. You can see limb asymmetries, meaning the morning side of the planet looks different from the night side of the planet. You can do transit timing variations where if that transit doesn't happen exactly periodically, there's a third body in the system and you can infer the presence of other planets. So it's the techniques have gotten better and also just the incredibly intelligent things we've been able to do with the data we have. People are so great at looking at this problem and being what else could we do with this?
It's really weird from my perspective. I only delved into the field of exoplanet detection briefly, but even during that short amount of time between doing planet detection one transit at a time to having something like the Kepler Space Telescope, now seeing the James Webb Space Telescope, and how it's enabling us to analyze these atmospheres is blowing my mind. And earlier on in the show, we spoke about future technologies like the Habitable Worlds Observatory that are being planned. Mm-hmm. I can't even imagine what this is going to do for our ability to find Earth-like worlds, let alone the search for life.
Yeah. So if you look back at kind of the history of NASA missions, Kepler really cracked it wide open in terms of planet discovery. We had never been able to put something that could measure light as precisely as Kepler in space before. And once you get above the atmosphere, you've solved 3/4 of your problem. It's good for astronomers because we can breathe, but it's bad for astronomers because we can't see the sky as well as we'd like to. So getting above the atmosphere was really important. So as you said, Kepler, we went from, hundreds of planets to thousands of planets. And Kepler, interestingly, did have a very specific goal of trying to find planets like Earth. So rocky planets in the habitable zones of stars like the sun. But actually, in the end, Kepler wasn't able to do that very well. It was a combination of stars just being more noisy than we expected. Their actual brightness was changing much more than we expected. And also the spacecraft having a few systematics that we didn't anticipate. So we didn't get there in the end. And so that's why we're thinking about Habitable Worlds Observatory, which is, what it says on the box. It's a big idea for a big telescope about 20 years from now. We're thinking real long term. About 20 years from now, a big telescope to take images of planets like the Earth around stars like the sun. And these would be very nearby systems. So some of our closest stellar neighbors are the ones that will be the target. Because with something like Habitable Worlds Observatory, where you're trying to take an image, you're actually trying to separate the star and the planet's light on the sky. So the closer the star system is to you, the further apart they appear on the sky. And the further away they get, the closer they are. So it's only nearby systems. And we're thinking we'll probably only be able to look at about 100 systems. So fingers crossed that Earth-like planets are quite common around sun-like stars in the habitable zone. And then in 20 years, Habitable Worlds Observatory will actually see them and take the light and spread it out and start to look for biosignatures.
We'll be right back after this short break.
The Planetary Society is strongly committed to defending our planet from an asteroid or comet impact. Thanks to the support from our members, we've become a respected independent expert on the asteroid threat.
So when you support us, you support planetary defense. We help observers find, track, and characterize near-Earth asteroids. We support the development of asteroid mitigation technology. And we collaborate with the space community and decision makers to develop international response strategies.
It's a lot to do, and your support is critical to power all this work.
That's why we're asking for your help as a planetary defender. When you make a gift today, your contribution will be matched up to $25,000 thanks to a generous member who also cares about protecting our planet.
Together, we're advancing the global endeavor to protect the Earth from asteroid impact. Imagine the ability to prevent a large-scale natural disaster. We can, if we try.
Make your gift today and join our mission to defend Earth.
Thank you.
I believe that Kepler, despite the fact that it was trying to find these worlds, it mostly ended up focusing on hot Jupiters just because of their size and how easy it was for them to detect. But we're now at this point where scientists are discovering just a much broader, a much more diverse population of exoplanets than we ever really anticipated. Are there any discoveries and new types of worlds that have really excited you during this career journey?
Yeah. So Kepler did look at hot Jupiters, but actually one of the really interesting things that it unveiled is that so far, the most common kind of planet, the planet we found everywhere around all kinds of stars and all kinds of orbits, is not a planet we have in our solar system. It's a planet that's bigger than Earth, but smaller than Neptune. In our solar system, there's nothing in between those two. So we have rocky planets, then we have ice giants, and then gas giants. And we found thousands of planets that are in between the size of Earth and Neptune. So now we're kind of left with very little information about what these planets are. So we don't know if they're big rocks or little ice giants, or you're asking about new types of planets. There's a hypothesis that they might be water worlds. So planets where like 50% of the mass, so half the mass, is made of a deep water ocean. And we think if you look at protoplanetary disks and the material that's available, these might actually be able to be created in the process of planet formation. You could create water worlds, and we just don't happen to have one in our solar system. So this would be a whole new type of planet with a whole new type of dynamics and interiors and atmosphere, a whole different idea of habitability, right? Like, what does habitability mean on a water world? So there's a few good candidates now where we've been able to measure the density, and we know that the density is consistent with it being a water world. And some of them we've even looked at with the James Webb Space Telescope and looked into their atmospheres to see if we can start seeing things like biosignatures. So that's pretty exciting. Water worlds is great. It's super cool.
I remember earlier this year, I was interviewing someone about the exoplanet K218b. But it's a debate as to whether or not I believe it's a Hycean world or if it's some kind of strange lava world or something. But they found a detection of dimethyl sulfate in the atmosphere, which on Earth we know only comes from, I believe it's life, but mostly life in the ocean, these kinds of plankton. That in and of itself blew my mind. It's not a definite there's life there, but the fact that we can even begin to make these detections and hypothesize about what might have created them is just amazing.
It's the process that's interesting, right? Like, how do you come up with the idea of a potential biosignature, something that couldn't be created geologically or chemically, needs to be biological, and then will it be created in a high enough quantity that we'll be able to detect it? And if it would, how would we detect it? What instrument, what wavelength, what type of measurement would we have to make? So the dimethyl sulfide headlines earlier in the year, I think were more illustrative of the process than an actual detection. Because it's not actually, I'm going to use air quotes now for people who are listening. A detection is a strong word because it's like 1 sigma, which in no field of science is 1 sigma detection. They weren't able to rule out dimethyl sulfide, which is interesting, right? They can't say it's not there. And then I will say probably since this interview, they have found dimethyl sulfide on a comet, on like a frozen comet in the solar system. So they're kind of like, okay, so maybe there's a non-biological way to make dimethyl sulfide. But this is the thing, right? You have to propose this idea, you have to test it, you have to come up with all of the potential false positive scenarios. And then at the end, you're like, yes, it passes all the tests, or no, it doesn't. And this is this whole framework that NASA has come up with now, because we're in this era. We get to start talking about what would life look like on other planets. So we need to have decision points and inflection points and thresholds for like, yes, it's passed all the tests. It's a sign of life. You don't want to tell the New York Times it's a sign of life and then a week later be like, oh, turns out we found it on a lifeless comet.
It's going to be really interesting to see which biosignatures ultimately we find on multiple worlds and be able to start actually comparing them. It won't actually tell us whether or not there's life there because there's so much we don't know yet. But by comparing that to things we find in our solar system, we could really unveil some mysteries.
Yeah, and I think that's part of the work for the next 20 years as we prepare for Habitable Worlds Observatory is to come up with like a library of potential spectra and atmospheres and biosignatures that it could see, so that when it has that, when it goes and looks at a rocky planet with atmosphere and finds ozone and oxygen and carbon dioxide, we can be like, the only way to make these 3 is life. But we have time to prep. This is what the time is for, to get ready.
It's not possible for any one person to know all of the exoplanets. There's so many of them. But if anybody had a chance, it would be you. Do you have any really like favorite worlds that you've found so far or that have been discovered so far?
So I am, as you're alluding to, I'm the lead scientist of the NASA Exoplanet Archive, which is how NASA keeps track of all of the planets we found. So I'm basically the keeper of the keys. I get to decide what goes in and what doesn't go in, which makes some people happy and some people mad because, everyone has their reasons. My favorite planet, I'm going to be very selfish, and it's a system that I helped discover. It's called K2-138. So the reason it's really interesting is it's because it's got 6 small planets in it. They're all kind of this sub-Neptune super-Earth size that I mentioned, this weird new type of planet. There's 6 planets, and 5 of them, the inner 5, are in a chain of resonances. They're all in 3-to-2 resonances with each other. So the inner one goes around 3 times for 2 times. The next one goes around all the way out. And these resonance systems, it's this new type of system that we found, these really tightly packed heaps of planets really close to their star. And the only way that works, the only way you can jam that many planets close in is if they're in resonance with each other. So it's like clockwork. They keep each other in place. So we do have some resonances in our solar system. So 3 of the 4 Galilean moons, for instance, are in a 1-to-2-to-4 resonance. So this is just a really cool system. And it's fun because the 3-to-2 resonance in music is the perfect 5th interval, which is the first 2 notes of Twinkle, Twinkle, Little Star. So it's like this system is singing, right? It's just a musical system. All these planets are in resonance singing a lovely song. And one of my favorite things about it is it was found by citizen scientists. So my colleague and I had set up a citizen science project to look through data from what became Kepler's sequel. So Kepler, the original telescope, had a couple of hardware failures, wasn't able to keep looking at the original field. And eventually we did an ecliptic plane survey. So we did 19 fields around the ecliptic. And that was called K2. That was Kepler's sequel K2. So we had all of this K2 data coming down. And my colleague Ian Crossfield and I started the citizen science project called Exoplanet Explorers. And citizen scientists could come on and help us find planets in the data. So the actual discovery story is kind of cool because we got approached by BBC's Stargazing Live, which is this annual television event that happens. And they make it sound really dramatic. It's like live TV. Let's cut to this astronomer. What are they watching on this telescope? And this kind of thing. So it makes it sound very, very cool. It's kind of like an action thriller astronomy program. And so they came to us and they were like, we'd like to feature a citizen science project. Can we feature yours? And we were like, absolutely. Because obviously the whole goal of success of a citizen science project is to reach as many citizens who want to do science as possible. And we're like, great, we'll be on the BBC Live. And so the first night we put all the data up and we had 2 million classifications immediately. It's a 3-night show. So the second night, the producers are like, we want something really exciting to announce tomorrow night. Can you find a habitable planet? And I'm like, no, because that's what the whole field has been trying to do for 20 years. I can't do it in one night. But I was like, what if we find a planet that what if we find a star that has multiple planets? Because one of the things you alluded to earlier is we have many more candidates than confirmed planets. And it's because these transit events we see, there's a bunch of different things that can cause them. The star itself can be noisy. The instrument can just burp, stuff happens. But if you see 2 different transit signals on the same star, that's much less likely to be a false positive because it's harder to come up with a scenario where the star is somehow doing 2 different things at the same time. But 2 planets orbiting the same star is pretty standard. We have heaps of multi-planet systems. So I went back to the producers and I was like, what about a multi-planet system? And they're like, sure, that at least sounds kind of jazzy. So I start going through the citizen science results and immediately the system pops out, which at the time they had found 4 planets. And I'm in the Slack, it's 2 a.m. in California. I'm in the Slack. Oh, look at this one. Here are the periods. And then Ian is like, wait, aren't they all in resonance? And I did the math and I'm like, oh my God, they are. So then we found a 5th planet on the resonant chain. And later, a year later, found a 6th planet. But we got to announce it on the 3rd night of the show. You guys found this resonance system. It's got 5 planets. It's super cool. So it was a big hit and it's a lot of fun and it plays music and it was found by citizen scientists. And it's got 6 planets. So that's my favorite system, K2-138, because it's fun.
It's a good one. It reminds me, too, a bit about how excited everyone was about the TRAPPIST system and all of those worlds and their resonance with each other. It's amazing how many of these there are. But, they have to be pretty close to their stars in order to actually achieve this kind of resonance. And it would be really fascinating to learn more about how these systems evolve. What got kicked out of the system as they formed that resonance?
Yeah, that's what a lot of people are working on right now. How do you build these resonant chains? That's what's happening in formation. It can't be too chaotic or they get kicked out of these chains. So something smooth and secular and slow is happening. And maybe they're drifting through the disk and catching each other in resonance as they go. And then those 2 drift and catch a 3rd one and those 3 drift and catch a 4th one. We're still trying to work it out. It's fun though.
And I love that you were involved in creating this Zooniverse project, because after I exited college and went on to do science communication, I missed detecting exoplanets. And the way that I did it was whenever I was stuck at a desk somewhere, answering phones, anything like that, I went to that project online and helped try to detect planets. And the community around it is beautiful too. The little notes everyone leaves each other as you're trying to discover. It's so fun.
Yeah, so if anybody's interested, the current planet hunting citizen science project that you could go and help us find planets in is Planet Hunters TESS. So now Kepler, even K2 ran out of fuel in 2018, but in 2018 we launched TESS, which is the current all-sky transit survey that NASA's running. And data are coming down from TESS all the time. And again, we need help looking through all the data. So Planet Hunters TESS is the current project. So if you go to Zooniverse and look for Planet Hunters TESS, you can help us find planets too.
And I'll leave a link to that on this webpage for this episode of Planetary Radio, just in case anybody wants to get involved, because it feels really satisfying. Because even if you have not a deep understanding of the science of the thing, you can still do a lot to help people actually sift through this data.
We have a lot of data and not a lot of people. Right? We are people constrained. So that's why citizen scientists are a great help. And especially at this early stage of just sifting through all the data, trying to pick out the good things. I mean, we have software that does this, obviously. And nowadays we have like AI and machine learning to try and help us do this too. But actually nothing beats a well-trained human sitting there and looking at the data with their eyes.
That's another point too, which is that we can actually make these AI and these machine systems better by studying how humans interact with the data. Like, so frequently we need people to actually do the initial work in order to train these large language models and other things.
Exactly. Yeah. So that's what we did with Kepler, for instance. We used all the human vetting as a training set to train the machine learning algorithm and be like, here's what people said was real planets and here's what they said was junk. You go and work out the rest.
Are there any particular discoveries that have surprised you or challenged your assumption about how planetary systems form?
Ooh, good one. So the resonance systems, I think, challenged me and a lot of people just because, that it seems counterintuitive to a lot of the ways we've thought about planet formation to create these like really dynamically packed systems where you could not put another planet in there without the whole system just exploding, right? It'll be chaos, dynamical chaos. So the resonance systems, definitely. I think things like the water worlds, right? We don't know what they are yet. I love the fact that Planet 9, the putative Planet 9, might be a super Earth or a sub-Neptune, right? Like if you look at the mass range, it needs to be where we haven't seen it yet, but it's big enough to shepherd all of these trans-Neptunian objects. It looks like something like a super Earth or a sub-Neptune. And I already mentioned that's the most common kind of planet. So you might think with 8 planets, it's weird that we don't have one. But maybe Planet 9 is one. Maybe we do have one. We just haven't found it yet. It's just in the outer reaches. So yeah, water worlds are really interesting. I think as we are able to characterize these planets in more and more detail, the fact that each individual planet is so different and interesting and, the amount of things we're able to find out. So for instance, there's HD 189733b, and I'll just pause here to apologize. Planet names are garbage. I'm sorry. I don't actually get to set them, but they're awful. It's just, it's an accident of how binary stars were named, and then planets were just kind of like small stars. Anyway, so HD 189733b, it's a very nearby hot Jupiter. Now, hot Jupiters, they're big, they're close to their star, so they're really easy to study in detail, especially if they're nearby. And this planet is one of the most studied planets we've ever found outside our solar system. So we've been able to measure the temperature, obviously it's so close to a star, the wind speed of the upper atmosphere, and that atmosphere has silicates in it. So what happens if you heat silicates up to thousands of degrees and blow them sideways? This planet is raining liquid glass sideways all the time. Like, just the fact we've been able to work this out, right? The fact that we know this planet is raining liquid glass sideways just constantly at like 2 kilometers a second. Like, you would just be pulverized. It would be super interesting, but you'd be dead immediately, nanoseconds.
It's wacky that we can even begin to look at the weather patterns on some of these worlds. People have discovered some really cool things about the types of clouds that they've found on certain hot Jupiters and things like that. But glass rain just sounds like the most beautiful nightmare.
Right. Yeah. And there's ruby clouds and sapphire clouds that people have found. There was one planet that we thought was a diamond planet for a while because of its C/O ratio and the fact that the core would be very high pressure. I think in the end, that high C/O ratio turned out to be a bogus measurement. But for a while, we had a diamond planet, which was cool.
That would be pretty cool. I mean, I've always thought of kind of white dwarves and all those degenerate objects, as a cool thing, but who knows what those kinds of objects look like. I'm assuming that degenerate diamond is totally different from a cool diamond world.
Right. It's not, you're not going to like whack it on a Tiffany's ring and be like, look at my cool diamond.
Given the advancements in exoplanet research, what are some of the biggest remaining mysteries that you're most eager for us to solve? And what would we have to do in order to actually get those answers?
Yeah, so one of the big mysteries for me is, we've done a really good job of investigating inner solar systems, like close to the star. But further out from the star, from about, Earth-ish out, from about 1 AU out, we don't have good constraints on how common different kinds of planets are. And so then we kind of fall back on our solar system, right? And we don't know yet, actually, right now in 2024, whether our solar system is normal or not. We don't know whether most stars have configurations that look like our solar system, like small inner planets and large outer planets. We don't know. We found lots of systems that have big inner planets. So there's this whole mystery for me of what the outer solar systems look like. And that's just as our techniques go for longer and longer, like as these radial velocity surveys and transit surveys go for decades, you start to be able to probe planets at those larger distances. And then the direct imaging technique, which, as I said, separates the light of the star and the planet on the sky, that at the moment only works for very hot, very big planets. And the idea is we need to get to cooler and smaller planets, and just the contrast ratio between the star and the planet gets harder and harder and harder to get. So one of the big mysteries is what do outer solar systems look like, and what do we need to do? We need to do better direct imaging and longer surveys, longer radial velocities and longer transit surveys. There's also going to be, NASA's going to launch a spacecraft in 2-ish years called the Nancy Grace Roman Space Telescope. First telescope named after a woman that NASA's launching, which is pretty exciting. But Roman, one of the things it will do is a microlensing survey. Now, we haven't talked about microlensing yet, but it's another way of finding planets, and it relies on gravity and gravity bending light, essentially. So if a star and a planet go between you and a background star, it magnifies the light of the background star. So what you're doing is looking at a background screen of stars and waiting for some of them to get brighter and fainter as a planet and a star go in front. It's kind of like magic. I'm pretty sure Einstein was the only person who ever understood how gravity bending light works. But anyway, we see it. It does work. Empirically, we see this happen. We see lensing. And so Roman is going to do a microlensing survey, and it will be sensitive to planets between like 1 and 10 AU, so between the orbits of like Earth and Saturn. So that's pretty cool. It's supposed to get down to Earth-sized planets. We'll see how far we go. I have the lucky position of being on one of the committee definitions at the moment and co-chairing that and trying to decide if we can actually design a survey to get down to Earth. So this is all literally happening right now. There's a meeting at 9 a.m. this morning to move this forward. So we're designing the survey that the Roman telescope will do to try and find outer solar system planets. So those are some of the things we can do to get towards outer solar systems. Like, my science interest is the demographics, right? Like, how common are different kinds of planets and why? Why are Earth-like planets common or uncommon? Why are hot Jupiters common or uncommon? What's the physics? What's happening in these protoplanetary disks to create this set of planets versus this set of planets? So for me, it's the demographics. Right now, the exoplanet field is kind of bifurcating. There's a small set of objects that we're studying in more and more detail individually with things like the James Webb Space Telescope and eventually with Habitable Worlds Observatory. So there's a small number of planets that are nearby that we're really staring at really hard with all of our instruments at all of our wavelengths to see how much we can find out. So HD 189733b is an example of that. But then the other half is, well, now we have this huge population. We have 5,500 planets. What can we say about the group, right? Like, what inferences can we draw about populations and what kinds of stars make what kinds of planets? So that's kind of this interesting like bifurcation right now. We're kind of getting out of the period of just like, hey, I found a new planet. Hey, I found a new planet. Hey, I found a new planet. Like, planet discovery is still cool, but it's really the science that we're interested in now. Like, can we find out more about it, or does it add to a population?
Have we made any actual discoveries around the idea that different types of stars might actually produce different types of worlds, or do we not have enough research on that yet?
Yeah, no, we're actually starting to find some really interesting things here. So one of the oldest results in terms of demographics and exoplanets is that stars that have more heavy elements, like basically everything heavier than helium, astronomers basically have hydrogen, helium, and then metals. So metal-rich stars, we already have known for a long time, make a lot of giant planets. So if you look at the distribution of giant planets, most of them are around metal-rich stars. And we actually didn't know for a long time how metal poor you could go and still build planets, right? Because the sun is kind of in the middle, but there's heaps of stars, especially anything older than the sun, that has fewer metals. So one of the results that's coming out soon, which is really cool, is being led by a student, now a postdoc, that I've worked with, Kirsten Bowley. We were able to use tests to measure where does the metallicity stop? Like, how low can you go and still make planets? And it's about a third the metallicity of the sun. Once you have less than a third the metals of the sun, you just can't make planets anymore. You don't have enough solid material in the protoplanetary disk to build planets. So that's really cool, because one of the things that tells us is that in the first 7 billion years of the galaxy, we didn't have planets yet, because none of the stars had that many metals. Galaxies are born very metal poor. It's just like a big cloud of gas. And then every generation of stars creates more metals, and those metals go into the next generation, and they create more metals, go into the next generation. So the whole galaxy is getting more metal rich with time, as every supernova creates more metals. So the earliest stars didn't have enough heavy metals to make planets, which is pretty cool, because now we get to start thinking about, this is fun, solutions to the Fermi paradox, right? So I assume you guys have talked about the Fermi paradox, which is, if there's life out there, where is it, right? Like the Earth is 5 billion years old, but the galaxy is 12 to 13 billion years old. Like, there's a lot of time for life to evolve, and if it could travel, take over the whole galaxy. So where is it? This is an interesting facet to that. Maybe the first 7 billion years of the galaxy, there weren't planets. Maybe they've only been around for the last 2 billion years. 2 billion years before we were around. So that kind of really closes that gap where the Fermi paradox is like, where is everybody? And it's like, well, maybe for a long time there wasn't anyone.
That's a really great point. And it makes me wonder, too, if as larger stars go supernova and ultimately as the universe kind of chills out over time, that probably means there is a point in the universe where there is peak planet formation.
Yeah, actually. So my husband is also an astronomer, and we are big nerds because we are married astronomers. We actually did this on a summer vacation like 2 or 3 years ago. We sat down and worked out when the peak of planet formation would have been. And we think it was actually 2 billion years ago, because that was, so the Milky Way goes through periods of strong star formation and then it quietens off. And so the last peak of star formation was a few billion years ago, and that was the most metal-rich peak of star formation that's happened. So we actually were just like at a beach house in San Diego with our kids, and when they went to bed, we were like, when is the peak of planet formation? And we sat down and worked it out.
You need to turn that into a paper.
I mean, that we should have, but we were on vacation, so we just wanted to know the answer.
Well, we're getting ever closer to understanding these populations of worlds and potentially having a better chance at detecting life on these worlds beyond our solar system. It's a hard thing to guess at, but given what you know about how this field has been advancing, do you think we're going to find life on a world beyond Earth at some point in your lifetime?
Yes, I do. I really do. And, it's, again, hard to draw statistical inferences from a sample size of 1. But if you look at the geological record, fairly soon, in astronomical terms, fairly soon after Earth was capable of hosting life, like the surface had cooled down and there was liquid water, we see life. Like, life emerges very quickly. And it doesn't get interesting and complicated and intelligent for many billions of years, but it emerges very fast, like within a few 100 million years, which sounds like a long time, but again, the galaxy is 12 billion years old, so a few 100 million years is nothing between friends. So I think that, if life is easy, we might find it. It might be that complicated life is hard, right? Like, simple life might be easy and complicated life might be hard. And thinking about solutions to Fermi's paradox, maybe simple life is everywhere and complicated life is not everywhere. And that's the filter. Maybe the filter is before us. Someone has to make it through and be aware of the fact they've made it through. Maybe it's us. It's so hard and so interesting to think about, right? Like, we don't know the end. And that's partly science, right? Like, you have a problem, you have a hypothesis, you work out how you're going to get there. So Habitable Worlds Observatory, for instance, is NASA's plan to get there. Like, how do we get a large enough sample of planets that we're sensitive to biosignatures on to start answering this question of how common are planets with biosignatures? And what does that mean for life? We don't know.
But we're finally having the technologies to actually be able to tackle these questions. I mean,
yes, this is the most exciting time to be in this field, I think.
It really is. I give it a couple 100 years and people will be like, oh yeah, we totally know all the answers to these questions. Like, this is like the new discovery.
Exactly.
We've barely touched on the beginning of all of these exoplanets, but you host a podcast from Caltech called Explore Exoplanets, The Discoverers. What is the show all about, and what do you hope listeners take away from it?
Yeah, so we're really excited. We're in the 2nd season of the show now. So there's 12 to 14 episodes out. So what I do is I interview people who've discovered exoplanets. One of the things I found is when I was giving public talks, which I love doing, people often cared a lot more about the journey and the emotion and the moment of discovery than, oh, cool, it's another hot Jupiter, right? And so I wanted to let people walk through that. Like, as scientists, the papers we write are very dry, right? Like, we observed this star on this night and got this data. Here is the result. But, when you're sitting there at the telescope and you're getting the answer on your screen as to whether this is a planet or not, It's amazing. There's this moment where you're the only person in the universe who knows that this is a planet, or at least the only person on Earth who knows that this is a planet. And it's those moments that I wanted to get people to be able to talk about, because they don't get to talk about it in their papers. But they're so exciting. And for me, like the thrill of discovery, you know, there's this saying that we're the generation that was born too late to explore Earth and too soon to explore space. I get to explore space. We get to find new planets. I have the coolest job. It's the coolest thing. So I wanted to let other people who've discovered planets get to talk about it too, and get to have listeners get to go on that journey. So we talk about, you know, how they found planets, how they felt when they found it, what are they doing now, what are they excited by? And then the second half of each episode, another thing that often happens is people ask me my favorite planet. And I really like talking about fictional planets, right? You know, science fiction dreamt of these incredible worlds decades, hundreds of years before we actually found them, right? So people have been thinking about fictional, incredible, brave new worlds for many, many years. So I really love like delving into science fiction and finding like real world analogs, because people have emotional connections to these stories. Like people grew up with Star Wars. When we found Tatooine, they were like, oh my God, we found Tatooine. And so I love using those emotional connections to teach people about science, right? Like we really found planets around binary stars like Tatooine. That's really cool. So the second half of the episode is I ask the interviewee what their favorite planet is and their favorite fictional planet, and we go and find it. We find the real world analog in the Exoplanet Archive, and we call it the carbon copy. So I really enjoy it, and I like the fact that people get to tell their stories, not just talk about the discovery itself.
That's a great way to get people to connect to the journey and also to the science fiction worlds that they know and love through their media. I mean, I would love to know if there's an Arrakis out there or a Trantor or, you know, what a cool way to get people into it.
We've done Trantor, but we haven't done Arrakis. We have found planets around red giants, so we're close to Arrakis.
We're close. Maybe by the next time the next movie comes out, we'll have found Arrakis by then.
Yeah.
Well, thank you so much for sharing some of your journey with us and for putting together this podcast, because I feel like every time there's a new exoplanet discovery, I want to bring it onto the show, but there's literally too many of them.
Yes.
So having a podcast that focuses on it is perfect.
Oh, thank you so much. Yeah. And, you know, I hope your listeners check it out if they're interested in hearing more. And thank you so much for having me on the show.
Thanks, Jessie. Now, let's check in with Dr. Bruce Betts, the chief scientist of the Planetary Society, for What's Up. Hey, Bruce.
Hello, Sarah. How are you?
That was so close to just hello, Clarice. It is so wacky how far we've advanced in exoplanet detection just in our lives. And I wanted to ask you what you think the field of exoplanet research is going to be like in the future, and what kind of evolutions of our understanding do you think we're going to see next?
Well, you've tapped into my expertise at being terrible at predicting the future, but I'm marginally better in space science than in the rest of the world. It's going to be huge, but it's going to be spread out over decades. So as you know, you talk about Habitable Worlds Observatory, it's off there in the future. But right now we're having these breakthroughs with James Webb Space Telescope. You've got these giant ground-based adaptive optic telescopes that'll be coming online. And so I think there are two places we're going to see it. One is in more discovery. But the other thing we'll be able to do that we couldn't do, as you probably discussed, was start to look at individual worlds and see things like what they're made of and atmospheres, and maybe someday kind of sort of image them, but at least get a lot more information about the actual planets themselves. Whereas now, largely we get the orbital period and distance and size, maybe, and then we make some extrapolations and do some modeling and kind of predict what kind of normal or zany world we have. There's a lot more focus even now using James Webb Space Telescope, and also with upgrades to Hubble and ground-based getting better and better to just study the actual worlds, and particularly with people focusing on those pesky, nifty, maybe Earth-like planets, at least kind of, sort of, maybe, because maybe they might have life. So anyway, that's where we're also going to be seeing is the fields of the searching for life and evidence of life blending. We're already seeing it blending with exoplanets, people from different expertise getting together. And in fact, some of them come together at the Planetary Society not that long ago, talking other worlds and what you look for and what you would look for with these bigger telescopes. So it's very exciting. I mean, it's like all of space science. There's a lot of patience involved as you get the elements in place. But once they're in place, the discoveries will be incredible, nay, unimaginable, at least in my little brain.
I'm sure it is going to be unimaginable, though. There are so many things about these worlds as we're exploring them that just defy all of my expectations. The first time I heard it might, rain diamonds on another world. You might have lava worlds like that. That is so intense.
Yes, it is. It would be. And again, a lot of modeling come out of that. But even in our solar system, every time we go someplace, we get surprised. There's so much to learn.
What I really want to know is if sub-Neptunes are actually the most common type of world out there. Because I honestly wonder if that's a limitation in our ability to find these smaller worlds, and whether or not that's actually going to hold true as we have new telescopes come online that can actually image these smaller worlds. Do you have a favorite category of exoplanet?
Kind of boring. I'm guessing you're going for diamond worlds and molten lava, but I just think the Earth-like planet, the Earth-sized planet, is something I can wrap my brain around. Rocky planets as opposed to exotic, hot Jupiters or something else. I am intrigued by what you've identified, the super Earth, mini Neptune type of planet, just because it doesn't exist in our solar system, and there seem to be an awful lot of them out there, and where transitions between rocky and gaseous, and what else do you get going on in that transition zone?
Finding a world like Earth of our size with liquid water on the surface would change a lot in the search for life, but the ones that have subsurface oceans really intrigue me just because they're so difficult to study. Like, I honestly wonder if most of the life in the universe exists in these oceans underneath ice shells, completely unaware that there's a broader universe out there.
Whoa.
Yeah, that's a trip. Well, before we go too far down the rabbit hole of tripping ourselves out, I did want to share a comment from one of our members in our member community. David Duthet from West Virginia was really excited about Asteroid Day and really enjoyed our episode about that, and said maybe they'll try chucking rocks into a sandbox to study impact patterns. Which I know sounds silly, but we actually did that crater demonstration at our Eclipse-O-Rama event back in April.
Yeah, no, and it evolved. People have been doing it for a long time. I adapted it into our Planetary Academy program that younger folks can get involved with and throw their own rocks, but that's probably not the right way to phrase it. People have, for a long time, have used things like light gas guns to fire objects at 6 kilometers per second and slam them into things to learn about impact.
Yeah, it's bringing back that memory about the Psyche mission, how they were trying to model how craters happen in metallic objects by just straight up firing objects at pieces of meteorites. That's the coolest job.
Yeah, no, it's pretty nifty.
Well, all right. What is our random space fact this week?
Random space fact.
All right. As of now, July 2024, there have been over 300 flights to the ISS, which is just stunning to me. Over 300 flights, more than 160 uncrewed supply missions, and more than 140 crewed missions.
Well, that gives us some hope. We'll just send one more up and we'll get everyone off of the ISS that got stuck there aboard this Boeing Starliner.
We'll see how that all works out.
But what an interesting time to be alive, where we even have to consider, oh no, one of our commercial spacecraft is still learning how to spacecraft. And now we got 2 people just hanging out on the ISS all day.
Knowing NASA, I doubt they're just hanging out on the ISS, but maybe. It would be a fun, the astronauts don't get a lot of recreational downtime. They're in the ISS, it's all groovy.
Right. One of those like, oh, I only have 10 days for vacation, and now I'm stuck here for 3 months. That actually sounds like fun.
It is yet another reminder that any group, whether country or private operation, pretty much has had a lot of challenges when they first go to space. And you can take, again, pretty much anyone. That's true. And a lot of them keep having troubles over time. So it's tough and it requires a lot of effort and a lot of meticulous everything. And when you start involving humans, all of that, because of they're humans, becomes so much more complicated, and you become so much more risk averse for good reason. And it's tricky.
Space is hard.
Which is why it's even more impressive that there have been over 300 flights to the ISS. Did you know that, Sarah?
I do now.
All right. All right, everybody. Go out there, look up in the night sky, and think about the clearest body of water you've ever seen. Lake, ocean, river, maybe. Thank you. Good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with a peek at the Australian Space Agency's upcoming lunar rover, the Rover. Love the show? You can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members who look up at the sky and dream of all the worlds beyond. You can join us and help advance humanity's quest to understand our place in space at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, Ad Astra.